In this video lesson, we're going to do the last two theorems, theorem 6 to 7. And as usual, just to remind you on how we do mathematics. Now, make sure that you understand both the examples and the proofs for the theorems, because that also just helps you to memorize it easier. And then when you see the pause button, make sure to pause and practice the question on your own, and then mark it and check where you made your mistakes if you do have something wrong. Right, now for the overview, so theorem 6 and its proof, and also questions on theorem 6, and then theorem 7 and its proof, and also questions on theorem 7. Now theorem 6 says the following: two tangents drawn to a circle from the same point outside the circle are equal in length. So basically what this says is we've got this point over here, a circle over here, and the point is outside the circle, and the tangents, the two tangents zx and zy, from the same point, they are equal in length, and that's basically what this theorem 6 says. Now when you use this theorem, then you use the reason tangents from the same point. Now to prove this theorem, we are given the following. We're given that O is the center of the circle, then we are also given that Z lies outside of the circle, and then we are given that XZ and YZ are both tangents. And what we need to prove is we need to prove that XZ is equal to YZ. Now in this proof, we're also going to do constructions, and we are going to construct the following three lines, the two radii, OX and OY, and then also OZ. And with these two constructions, we can see that two triangles are forming, and to prove that XZ and YZ are equal, we are going to prove the two triangles is congruent to each other, which then basically can conclude our proof in saying if these two triangles are congruent, it means that the two corresponding sides will then be equal. Right, now first of all, we're going to say in which two triangles we are working, in triangle XOZ and triangle YOZ, and then list out three things that are equal. The first thing we can see is that angle X is equal to angle Y, and this is another thing. If you have a radius at that point on the circumference where the tangent touches the circle, and the line between that point and the center of the circle, which is obviously the radius, these two lines, they form a 90-degree angle. That is a general case. So we know that these two angles are equal because the radiant is perpendicular to the tangent. Then we can see that OX and OY is equal because they are both the radius of the circle. And then finally, we can say that OZ is equal to OZ. It's a common side to both of the triangles. Okay, so that is our three things, and therefore we can say that triangle XOZ is congruent to triangle YOZ. And our reason is right angle, hypotenuse, and side, because we've got the right angle, the hypotenuse, and an alternative or an extra side. And then we can simply conclude that XZ will be equal to YZ. Okay, so that was theorem 6. Now moving on to its questions. In example 8, it says calculate the length of D. Now there's two ways to do this, because we can choose whether we want to work in triangle JIH, or we can use triangle JGH. Okay, if we do the above triangle, then we're just basically going to say that JI is also 5 because that's a radius. We also know that the angle between JI and IH is 90 degrees because the radius is perpendicular to the tangent. But for this video, I'm going to work in JGH, just simply for the reason because we are working with theorem 6, which states that the tangents from the same point are equal. Okay, so to find a GH, we can see that that's just simply going to be 8. So tangents from the same point, and then we can also say that angle JGH is 90 degrees, and if that's 90 degrees, we can use Pythagoras to find D. Okay, so let's do that. So starting off, we're going to say GH is equal to 8, and that is just tangents from the same point. Okay, and then I'm going to say that JGH, that angle is equal to 90 degrees because the radius is perpendicular to the tangent. And then we can use Pythagoras. So we're going to say that d squared is equal to 5 squared plus 8 squared. And our reason is Pythagoras. Okay. And then d is equal to the square root of 5 squared plus 8 squared. And just calculate that on the calculator. So square root 5 squared plus 8 squared is the square root of 89. And if we do that to 2 decimal places, we say SD 9,43. And in this case, they've given us units, so we're going to say centimeters. Now for question 8, calculate the length of E. So E is over here. Now, how do we do that? So basically, what do we need to calculate E? If E is in this triangle OMN, and we know this is a right angle triangle because the line LN is tangent and OM at that same point is the radius, so they basically form a 90-degree angle. Now, if we can have OM, that length, and we can have MN, then we can basically use Pythagoras to solve for E. So OM is pretty simple because that's the radius, and we can see the radius here, OK, is 2, so this is also going to be 2. Then we are given that LN is 7,5, and if we can find LM, we can just subtract the 2, and that would leave us with MN. And then we can use these two sides together with E and Pythagoras and solve for E. So we can find LM because it's the point from the tangents from the same point. So that means that LM and LK are equal. So that's also going to be 6. Okay. So basically that is the solution. So let's just put it on paper now. So we're going to start. I'm going to start over here and say, okay, LM is equal to 6 because it's tangents from the same point. Okay. Then I'm going to say that OM is also 2. And that is the radii. Next, I am going to take LN and subtract. We can just basically mention that LN is equal to 7,5 and that it is given. All right. Then we're going to say, okay, but then MN is equal to LN, which is 7,5 minus 6. So this is going to give us 1,5. All right, so this is 1,5. Now that we have both those sides, we're just going to use Pythagoras. So we're going to say that E squared is equal to 2 squared plus 1,5 squared. And the reason is Pythagoras. And then E is the square root of 2 squared plus 1,5 squared. Let's type that on the calculator. Square root of 4, I'm just going to say 4 plus 1,5 squared. And that gives us 5 over 2 or 2,5. And our units is in centimeters. Now for example 9, calculate the size of A, B, and C. Okay, so A is in this triangle, TAP. But this triangle, we can see that P is a point outside the circle, and these tangents run from P, so meaning that this is tangents from the same point, so they are going to be equal, okay? Which makes T3 equal to A, because equal sides equal angles, right? So I can start off and say that TP is equal to AP. It is tangents from the same point. Okay, and then that makes T3 equal to A, and equal sides equal angles. And now I can use these three to solve for A using angles of a triangle. So A plus 50 add up to 180, where we have angles of a triangle, and solve for A. So 2A, and then take the 50 over to the other side, would give us 130. So 180 minus 50. Then divide both sides by 2, so A will then be 65 degrees. Okay, so we've got 65, 65. Next we need to find B. Now, to find B, it would help to find T2 and A2, or just one of them, because they are equal. And why are they equal? Because OT is equal to OA, which is the radius. So this is equal to this, okay? But we can find A2 because this is the radius, BA is a tangent, and they connect at the same point, which means the angle between them will be 90 degrees. So I'm going to say that A2 plus 65 degrees is equal to 90, and the reason is that the radius is perpendicular to the tangent. Okay, and then solve for A2. So A2 is equal to 90 minus 65, and that would give us 25 degrees. And then I'm going to state that OT is equal to OA because of the radii. And then we can say, therefore, T2 is also 25 degrees because of equal sides, equal angles. And then solve for B. So using angles of a triangle, B plus 25 is equal to 180 degrees. And the reason is angles of a triangle. And then B is basically, if you take the 25s to the other side, it becomes minus 50. So 180 minus 50, that gives us 130 degrees. Right, so this then is 130 degrees. Now to find C, that's pretty easy because we've already done a theorem that says that the angle at the center of the circle is twice the angle at the circumference. So simply to find C, we can just halve this angle, and this is going to be 65 again. And our reason is angle at center is 2 times the angle at the circumference. Right, and then we're done with that one. Right, now for question 9, calculate the size of x, y, and z. So let's start with x. Now, x is in an isosceles triangle, So this is quite easy because these two angles are equal to each other. So we can simply start off by saying that x is equal to 30 degrees because of equal sides, equal angles. Right? Y is also simple because we've got now angles in a triangle. So that's y plus 30 degrees plus 30 degrees is equal to 180 degrees, angles of a triangle, and just solve for y. So y is equal to 180 minus 30, so 180 minus 60, and that gives us 120 degrees. Okay, so this is 120. Now for z. Now z forms the triangle CDB, okay? And we can see that C is a point outside the circle, and it is formed by 2 tangents from the same point, which means these 2 tangents are equal to each other, okay? So I'm going to say that DC is equal to CB, or BC, because of tangents from same point. And what can happen now is we've got these 2 angles which are equal. So if we can find basically one of them, which we already have, we know that DBC should be 30 plus 30. So DBC BC is equal to 30 plus 30, which is equal to 60. And then we know that CDB should be equal to 60 as well, because equal sides equal angles. Okay, now we've got two of the three angles, and we can then solve for Z. So Z plus 60 degrees plus 60 degrees is equal to 180 degrees because of angles of a triangle. And then to solve for Z, we just take the 60s to the other side, and we're left with 180 minus 60 minus 60. This gives us 60 degrees. All right, then we're done there. Okay, so this was Theorem 6 problems. Now let's look at Theorem 7. And Theorem 7 says the angle between the tangent to a circle and the chord drawn from the point of contact is equal to the angle subtended by the chord in the alternate segment. So what is this saying? This is saying that JH, which is the tangent, and this JK is a chord. Now this angle between the tangent and the chord, which forms, is the same as this angle over here. And this angle is the angle that's subtended by that same chord. Alright? And that's basically Theorem 7. So if you use that, you just simply say it's the tan chord theorem. Now the proof, there's two proofs for this theorem. So the first one looks as follows. Now in both cases we are given that O is the center of the circle, JK and L are points on the circle, and then JH is a tangent to the circle. And we need to prove that KJH is equal to L. Basically what we saw, that this angle is equal to this angle. Now as in previous proofs, we are going to make a construction, and the construction lines we are going to draw is OK and OJ. Now also before we start, I'm just going to tell you first where we are heading or what we are planning to do, and then I'm going to do it here. So first of all, we're going to make L, or let L equal to X, alright? Then what we're going to do is just use our normal rules that we know, even the previous theorems that we know, to find, to see if we can show that J1 is also equal to X, right? And that's basically it. So we're going to start by saying this angle is twice X, and then we're going to say that this is the radii, so meaning these two angles are equal, and then find J2 in terms of X, and then find J1 in terms of X, which should also be X. Okay, now next we say that JOK is 2X, so this is 2X because it's double, the angle at the center is 2 times the angle at the circumference. And then we're going to say, okay, but this is equal to this. We've got OJ is equal to OK because this is the radius, which means that those two angles, J2 and K1, is equal. Although we're not explicitly going to say that, this statement over here is basically, it comes from saying that J2 plus K1 plus 2X is equal to 180, where it's angles of a triangle, and then replacing K1 with J2, and then solving for J2 basically. So 2J2 is equal to 180 minus 2X, and then just to simplify it, we divide everything with 2, and that leaves us with this angle, which is 90 degrees minus X. Okay, and then we know that the radius and the tangent forms a 90-degree angle. So you're going to say that J2 plus J1 adds up to 90, okay, but J2 is 90 minus X. So we're going to say that J1 is J1 is 90 minus J2, okay, and if we simplify that, it simplifies to X, so we can say that J1 is equal to L, and then we can just end off and say that therefore L is equal to KJL. And that concludes the proof. Now the proof, the similar proof, the only difference here is you'll see that in the previous case, we had our center inside this triangle, okay? And that means our lines that were constructed were also inside the triangle. But in this case, our this is a proof for whenever the triangle is out, or the center of the circle is outside of the triangle, okay? And again, we are given the same. O is the center of the circle, JK and L are points on the circle, and JH is a tangent to the circle. And what we basically need to prove there, like we saw earlier, is that KJH is equal to L. So this angle must be, we must prove that equal to this angle over here. And so the construction lines that we are going to draw again is OK and OJ, but now our diagram just looks a bit different, which is going to make our geometry or calculations just slightly different than in the previous proof. We are still going to make this equal to x, and then try and work our way through to J1 to prove that J1 is also equal to x. Okay, and most of the procedures are going to be the same still. So we're going to still say that this angle is twice that angle, because of angle at the center of the circle is 2 times angle at the circumference. So we let L equal to x, and then we say that O1 is 2x. Now to find O2, we just basically use angles around a point. So O2 is 360 minus 2x because of angles around a point. So I'm just going to write this in. And remember, as I said in an earlier video, when you do this proof in an exam, you are not required to make these notes, although it wouldn't be wrong, it might just help you. But what is required is that you have these construction lines in. You construct that, you get a mark for that, and write down that you constructed OK and OJ, and then write out your proof as it is on the right hand side. Okay, but I am just doing these notes in yellow just to give you more insight on what's going on. Okay, so this is 360 minus 2x. And then we can say, okay, these are the radii, OK and OJ are radii, so they are equal, which makes the two angles equal. It makes KJO equal to JKO. So again, a lot of steps are left out here, but to find KJO, or J2 in this case, there hasn't been a 2 there, but to find J2, we are going to say this angle JKO plus J2 plus O2 adds up to 180, and then you replace this one. Now this is the full proof. You don't actually have to do that, but I just need to explain to you where this comes from. Okay, so then solving for J2, we say, okay, 180 minus this angle, and simplify that, and then divide it by 2. So simplifying this, dividing it by 2 leaves us with J2, the small angle, equaling x minus 90. Okay, now furthermore, we know that this is the radius and this is the tangent, so that is a 90-degree angle, and then the reason radius is perpendicular to the tangent. And then we can say, okay, this entire one that we wanted to prove, KJH, is then simply just the J2's value plus the 90-degree value. And then if we simplify that, that leaves us with x, which is equal to L. And that is then our proof in this diagram. Alright, so Theorem 7, now all we need to do is just the problem sums on Theorem 7. So for example 10, we are going to calculate the size of A and B. Okay, very straightforward. A, we've seen in this theorem that this is our angle between the tangent and the chord, and this is the angle that is subtended by the chord, so that means they are equal. So A is equal to 33 degrees, and my reason is tan chord theorem. Okay, and then we've got B. Now also what we also given is that these lines are run parallel to each other, meaning that B and the 30-degree angle, which forms a Z, that is alternate angles, so meaning B is also equal to 33, and our reason is alternate angles, whereas FG is parallel to CD. Now for question 10.1, calculate the size of I, J, and K. Now I is pretty easy. We've got angles on a straight line, so it's just going to add up to 180. I plus 121 degrees plus 19 degrees will equal 180 degrees because of angles on straight line. And then to solve for I, we just subtract on the other side. So this is 180 minus 121 minus 19. Okay, and they are together 140, so 180 minus 140 is 40 degrees. Okay, so I is 40. Then to find K is pretty easy because these two angles are equal to each other with the tan chord theorem. So K is also equal to 40 degrees with the tan chord theorem. Okay. And then finally J also. Now we can find J in one of two ways. We can use angles of a triangle, but that's going to be a longer way. We can simply say that 121 degrees is equal to J because of the tan chord theorem as well. So J is equal to 121 degrees tan chord theorem. Then for question 10.2, calculate the size of PQ and R. Now, P in relation to 52 degrees, this is the tangent, this is the radius, and we know the tangent and the radius are perpendicular to each other. So meaning that P and 52 must add up to 90. So P plus 52 degrees is equal to 90 degrees. And we can state that that is the radius that is perpendicular to the tangent. Now to solve for P, P is equal to 90 minus 52, and that's just going to give us, so 90 minus 50 is equal to 40, so it's going to give us 38 degrees. Okay, now that's 38 degrees. Okay, next up to find Q. So Q is straightforward because Q and the 52 degree angles, that forms the tan chord theorem. So Q is simply going to be 52 degrees. Tan chord theorem. And then finally to find R, again we have two options. We can use angles of a triangle, or we can notice that O is the center of the circle, which makes UR the diameter, and whenever an angle is subtended by the diameter, it is equal to 90 degrees. So R is equal to 90 degrees because of angle in semicircle. And we're done. Okay, now for example 11, calculate the size of X and Y. So X lies over here, Y lies over there. I have a center of the circle over here. We can see this angle is subtended by the center of the circle. We have a 40 degree angle and a 95 degree angle. Now, first of all, to find X, we can see this is our chord and this is our tangent. And then the angle that's being subtended is X, which means that X is equal to the 40 degree angle. So we've got X is equal to 40 degrees. And we've got the tan chord theorem. Okay. Now for Y. Now let's look at Y. There is actually a very long way to do it. We can say that, well, basically we can see that this big angle here subtends this big angle here. So basically we can find this angle, add them together, and then we have this big angle, which equals that big angle. Then we subtract X from it, okay? But a much shorter way is actually just to find D1, all right? We know that this is a 90 degree angle because of this diameter. And if we have D1, we know from a previous theorem that D1 and Y must be equal because they are subtended by the same chord. Okay. So to find D1, we're going to say that D1 plus the 59 degrees is equal to 90 degrees because that is angle in semicircle. Okay. Now to solve, we just say D1 is equal to 90 minus 59, so 90 minus 60 is 30, so that's going to be 31 degrees. Right, and then we can simply say that y is also equal to 31 degrees, so y is equal to 31 degrees, and our reason being angles in the same segment. Okay, so that was easy enough. Okay, so for question 11.1, calculate the size of x, y, and z. So x over here, that actually is subtended by this chord FD, all right? And the angle between FD and AB is 130, so we can actually apply the tan chord theorem and say that x is equal to 130, just simply because of the tan chord theorem. Okay. Next, we can solve for z first, actually, before y, because of the angles on a straight line. Okay, it looks like this indicated that z is this entire angle over here. So using angles on a straight line, we can say z plus 130 degrees is equal to 180 degrees, and that is angles on a straight line. And then that makes z equal to 50 degrees. Okay, and z and y is also equal to each other because of the tan chord theorem. Okay, because we've got this FD chord again, and this angle between the chord and the chord and the tangent is equal to the angle that's subtended by the chord. So y is equal to 50 degrees because of the tan chord theorem. Now to calculate for x and y. Okay, so we have this angle over here. We've got a 38-degree angle over here. We've got a smaller circle and a bigger circle, a larger circle. But both of these circles have the same tangent, AB. All right. So from the first one, I can basically see that this angle over here, D1, is equal to 54 because of the tan chord theorem, but this angle is also equal to x because of the tan chord theorem. Okay, now be careful. We can obviously see now that, okay, x is 54, which makes these lines parallel, but you can't just use that in the beginning. You can't just say, okay, x is equal to 54 because of corresponding angles, because nowhere do they actually tell us that these lines are parallel. And if they do not indicate it, even if it's accurately drawn, you cannot use that, okay, unless they've told they told you that it's parallel. All right, so I'm going to start and I'm going to say that D1 is equal to 54 degrees, tan chord theorem, and then I'm going to say that x is equal to 54 degrees, tan chord theorem. Okay, now for y. So there's two ways. First of all, we can use angles of a triangle to find J1, and then angles on a straight line. But that's unnecessary work because we can just simply go straight ahead and use exterior angle of a triangle, whereas the exterior angle of a triangle adds up to the interior opposite angles. Okay, so we've got y equal to 54 degrees plus 38 degrees, and that is because of exterior angle of a triangle, and y is then equal to 80 plus 12, so that's 92 degrees. Alright, so we are done.